some saturation, so I'd like to start. Also because it seems always anyway behind time. I do not waste additional minutes by waiting. Also, I think it's also not very polite for the online crowd. I have 3 announcements or 2 to make in the beginning. First of all, that's mainly interesting for the people physically present on site. We will do they will be taking a photograph at 12:30 in the courtyard. So please be aware, go to the bathroom before, prepare yourselves, right? 12:30, there will be a picture taken. And then the second more scientific thing, I'm not sure if it's readable online, but please send me an email if you can't read it, or I can try to remember to put in the chat later on. There are 3 references on the board. So there were questions regarding batches, how you can cleverly in parallel evaluate samples in context of sequential design. And these are 2 papers. So the first one is by Julian Becht and co-authors, and the second is from our group. I put the archive links or the archive numbers because they are freely available. That's good, right? And they're shorter than DOIs, so that's another advantage from me on the board. But they all both are published in proper journals, so they are somewhat trustworthy, I would say. And then I put a link regarding multi-level Monte Carlo methods. This is like the very fundamental paper by Giles. But honestly, if you're interested in that, it's super easy to find, right? If you Google multi-level Monte Carlo, you will find something. So those papers are difficult or more difficult to find because the titles are not so obvious, I guess. But I mean, if you Google Giles and multi-level Monte Carlo, you will find a lot of very nice papers. So if that's interesting for you. So in that sense, this DOI is maybe not as relevant because it's not so well hidden like those. Okay, these are things I want to say in the beginning. So I mentioned that I'm a bit short with time, so I will do selections of the stuff that I plan to show in the beginning. And let's start with some material that is really more application oriented, but I think that gives some understanding how these concepts that I showed are put into place and how the algorithms could look like. Yes, so it's joint work with several colleagues. So from Theo Braunschweig again, then there's a former PhD student of mine who's now at Carl Zeiss. That contains material that they worked on in their respective PhD thesis. Okay, the pointer seems, no, yes, it works, perfect. Okay, so the first 2 case studies I'd like to present. So I may skip this part just to save a bit of time, but in the first case, I will talk about this kind of this yield concept where we used also Gaussian processes, and I think it's very natural and it shows immediately why this concept is very interesting. So I talked already about the yield, right? So it's a specific measure where you want to evaluate the probability, let's say, that a failure does not happen. So in stochastic terms, the yield means 1 minus failure probability. So both concepts exist, right? You either want to minimize failure probability or you want to maximize the yield. Different communities choose different formulations for that. As I said before, so it's not so much like the question of possibility, it's more a question of money that you typically do not have production processes which really yield 100% of working products, but just maybe a very high 90% fraction. Now it depends what is for you let's say the point of break even, right? Where it's attractive to place your company or your production process. This originally comes from the chip industry. I think Motorola was one of the first companies to establish also the Six Sigma design, and these kind of topics come. That's like the story behind this. Okay. Now let's suppose we are in a 2-dimensional setting, just because it's easily visible or more easily visualizable on a slide. So we have now 2 random parameters that affect my process, and they may be randomly distributed, right? And they may be somehow normally distributed, and this may look like this, right? And their expected values lie in the center, and then you can draw samples. And now these samples, of course, are computer samples, but you also imagine that these can be products, right, in some space, and then you have these different realizations. I mean, by purpose, we didn't put any axis labels, so it's of course arbitrary, right? But that could be like a millimeter variation in some radius of whatever product you think of, that is maybe in the size of meters or whatsoever. Okay, then we talked about this deterministic design parameter. I talked about this range parameter that we have. So D we can modify, and R maybe some additional boundary conditions on which we want our product to work. And then we have some goal function, it's or quantity of interest that I note here with, or KPI, different names exist, and they form what is called in industry, or in some industries, a performance feature specification. So somehow the quantity of interest shall be smaller or equal than some constant. And this is a feature specification. And this may be a thing that you have agreed on with another company that wants to buy something from you or whatsoever. And then we define two domains. So there's the so-called safe domain, which contains all the products that fulfill this, and there's the remainder. And this, of course, you don't know this boundary exactly, right? If you would know this boundary, our life would be much easier. So this black line, I mean, this exists, right? It's implicitly defined, but we don't have access to this. There are actually also methods which are called geometric methods that really try to recover this line in the parameter space. We looked into that, we didn't like them, so we didn't follow that path. We rather follow the stochastic approach, which will be based on sampling in the end. If you're interested, I mean, we can also discuss about that a bit more, but our experiment and also my feeling was reconstructing such a surface in an n-dimensional space is a very tedious job to do. I mean, you can, if it's, many people work with linearizations here, if that's possible, okay, then I see how that could work, right? But in a more general setting, I think it's a tedious job and not very reliable to my feeling, so that's why we didn't follow this path. So but again, they're called geometric methods, and for example, in the book of Helmut Greb, you can find more on this. Okay, so then what you have to do, we have to compute now, we evaluate for each of those samples whether it fulfills our requirement. Then we either return a 1 or a 0, so that's an indicator function over there. And then we sum it up, yeah, or we integrate. And this gives us the expected value of this characteristic function, and this is then the probability that we are looking for. Okay, so in the end, this is not so much different to computing pi, right? I mean, you showed you this example. It's a similar task than this, right? So I don't know. The screen doesn't like pi. So we don't know the boundary, we don't know the value of pi, right? But we can evaluate whether we are inside or outside something. So this is super simple, that's great. It's easy to implement. It has good accuracy, but has rather slow convergence. And I think I will discuss about that a bit more in the optimization part, but maybe I can already say 2 words about it. The issue with this is that you may have what's called tails, right? The ends of the normal distribution. And it's known that if you have a surrogate model, it may perform quite bad actually on the tails of the distribution. So in these kind of situations where this may be relevant, where you may deal with very rare failure probabilities, or you hope so actually, that many surrogate models are not performing well. So in these kind of situations, you really need what I will later call a hybrid method, where you really make sure that you don't do bad evaluations that give you, in the end, wrong results. And that goes back to ideas from Dongbing Xu and his group. So the idea that the Monte Carlo method is bad. Sorry, that the surrogate model is bad, and well, the pure Monte Carlo method would be good, but it's very expensive. So the idea that they came up with was the following. So you evaluate only a subset of the original model, and then you use a surrogate model maybe for the others. But then the question is which kind of surrogate model you can use. And what are the so-called critical samples that are the ones that you actually evaluate on the original model, and for which can you use your surrogate. And what we do is, so we tested 2 technologies, let's say. For both cases, I mean, that's essentially the 2 papers regarding this. So in either way, it's important that you have some measure of accuracy. So let's suppose you have a surrogate model now, so you have an original function, and then you have a surrogate with a tilde on top. And now if you know how much you can trust your surrogate model, so then you can decide how far am I away from this performance feature specification. So if I want to evaluate here and I have some error bounds or indicators epsilon, okay, I can say, well, this sample I can trust so much. But either way, I mean, whatever happens in this interval, I'm fine, right? I'm sufficiently far away from my original constraint. And this would be maybe a good one, okay? So, and this guy would be sufficiently far away on the bad side of things, so, okay, that's bad. I don't need to do anything extra. But what about this guy? So this guy is on the good side, on the bright side, but on the other hand, we are not really sure because our surrogate may be not very accurate. So this is a point that I will not use my surrogate, but I like to evaluate the original finite element model, which is very expensive. And what would be very interesting, and that's already where, if you have the creativity or you follow the line of thought of my lectures, this is interesting for Gaussian processes, for example, right? You get some random additional point, which is not necessarily lying on some grid or something. So you get a new point, you realize, okay, at that point, I don't know my surrogate very well. You evaluate that on an expensive model, and now it would be very great if you can use that to train the model, right? Because you may expect that, I don't know, it would be this guy. Oh, I should use a pointer for the online crowd. So this blue point there, I realized, most probably would be some on the boundary. Okay, let's pick that one. So here, my model is not sufficiently accurate. So then I will add this to my training set, and then I can hope that, for example, that point in the neighborhood that I maybe evaluate afterwards has been a higher accuracy, right? And I do not need to do another finite element in simulation to evaluate this point. Okay, that's like the reasoning behind, and that works actually quite well. There are two things that can happen, right? These kind of points, you have to evaluate are either very close to that boundary, or they have very large uncertainty or error in the surrogate model, to put it like that. These are the two cases that can happen, and in both cases you would add additional points. This is a bit related to in Bayesian optimization. I would say this is rather the case where you are in the exploration phase. I mean, you haven't seen that part of the curve maybe, so that's why you have a large potential error. And this one is rather because you are so close to the boundary. Okay, so what kind of surrogate models you can take? So the winner, I mean, I will show you two examples, but I think the winner in the end was Gaussian process regression. So we talked about that, so I can be quick. You have seen those images, and I will do them just quickly again. But this is really data from 1D example we did in this context. So what we did here was we used the GPR mean as our prediction, so as our surrogate model, as our response surface, and then we took the standard deviation from the GPR as a measure of error. So essentially, this gray zone was then the safety zone we used, and we used a factor of 2. Well, why did we choose a factor of 2? Because it worked. So, I mean, I cannot promise this, right? This can be chosen. You can choose any safety factor you want. So as maybe you remember, so the idea behind that this is a Gaussian distribution, right? So this is the standard deviation. So in that sense, like very statistically speaking, you don't have any, you can't be sure that the points or that the accuracy is actually in between these boundaries, right? Just very, very, very likely. And the larger you choose that number, the higher the likeliness. But I think also it's not surprising that if I choose this number too large, I will force to evaluate more and more and more points, right? Because if I choose that number larger, so let me go back, because I have seen some faces that look not too happy. If I choose that number larger, I make that interval bigger and bigger and bigger, right? Which increases the probability that I will do additional evaluations. And at some point, I will just do plain Monte Carlo because and then I didn't gain anything in the end, at least computationally. I'm sure that all points are properly evaluated, but I need months to do this. Okay, yeah, I think that is clear. So the alternative, that's where the Braunschweig group comes in. We did this also with a polynomial approach, and there we used an adjoint error indicator. That's another possibility you can do to estimate the errors. So this is mathematically maybe a bit more rigorous, I would say. However, the drawback of this approach, I would say, is that you cannot so easily add new points to your polynomial model. You may remember that I said that typically if you use these polynomial models and you have a piece of chalk, they are based on grids, right? So I could start creating such a grid. I could evaluate on that grid, and I could create my response surface. But then I get this new points there. So what to do? I cannot just easily add that to my polynomial. And so the polynomial cannot learn from additional finite element evaluation that you do, at least not easily. And that's why. And additionally, the adjoint error estimator needs some it's intrusive, I would say. So you cannot use that with any black box code. That depends. I mean, if you use a commercial software, for example, it depends whether they implement it for you at joins or stuff like that, right? And you cannot rely on that. So that's why this approach is also, let's say, more black box. And these are two nice advantages. But I would somehow say this is more or less the winner of the story. Okay, what we did was a very simple electromagnetic example. It's a waveguide. Don't bother too much. It's a simulation task where we looked at something called S parameter. And we looked, this S parameter should fulfill some criterion. It depends on the frequency, so we sweep the frequency and wanted to stay below that black line for the frequency of 6 to 7 gigahertz roughly. And you see that these approaches are super effective. So I said that it brings really down from weeks or months to days. So and this is the outcome. Those two methods have slightly different number of evaluations. I would say that we even saw, I mean, I cannot prove this, but I think we saw, I would argue we always saw that, like this kind of pattern that this means stochastic collocation, which is essentially the polynomial approach, right? That this takes a bit more points because the model cannot learn along the way. So on the online part of the method, there's no learning. On the other hand, I'd say, I mean, look at this comparison, maybe that doesn't matter too much anymore. I mean, still, if a single evaluation is very, very expensive, this is almost a factor of 2, right? So that can be crucial for you, but compared to this, okay, it may not matter so much. But still, they significantly reduce. Yeah, you see that now. I mean, for this simple model, this was 9 days, and this was then in just a few hours left to do this. Okay, yeah, so I think that's the summary of the stuff. So both very effectively reduce the number of evaluations. I mentioned already that this approach is non-intrusive, so you can use that with any black box software. You could update the model. That is not so easily done here. If you remember what I said last time, so one thing you could do at some point, you could start also doing regression here. You could do polynomial regression, but we didn't try this one. Yes, this error indicator comes almost for free in the Gaussian process regression case. Sorry, but it's not, let's say, it's a bit more effort for these polynomial approaches. Okay, and if you're interested, I mean, actually this is surprisingly simple to, I mean, if you have a tool that creates Gaussian processes for you, it's actually quite simple to implement this method. Okay, so that's for my first case study. Other questions? Does it make sense? Yes, please. Yes. 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 So the question is, I mean, the statement was that in the paper, the original paper that I quoted from the group of Chu, that there's a proof of convergence, and I didn't read that paper. I mean, I think I agree. I don't read the paper yesterday, so some time ago that I read it. I would claim that this method has the same properties. So I mean, we didn't prove that. We didn't even try to prove that. We didn't think about proving it. But my understanding is that we just exchange one part of the method by something else. So we exchanged essentially, I mean, Dongmin Chu was also using rather this polynomial-based stuff, but if I recall correctly, he didn't have a proper error estimator at that time. So he did, I think, I'm not sure if I should say that even there's online crowd available, but I think it was a quite crude approach to check for the accuracy. And so the one paper we did with these adjoints was already an improvement, I would say. And I think we should inherit all the nice properties. I think from that paper, and unfortunately I put that part in the optimization lecture, there's even a very nice example that shows what is the issue with these surrogate models. I will maybe come back to that question later. But yeah, I don't see any reason why there should be a loss of anything in convergence. I mean, so also maybe for the mathematically interested crowd, you typically distinguish between error estimation and error indication, yes? So the question is how much, I mean, how sure are you that you really fulfill those errors, right? I mean, and actually also with, so that's why I said, also here, check, it's called indicator, it's not called estimator. So it's not, these bounds are not guaranteed, neither here nor there. And that's where these methods, of course, can fail, right? If this error bound is not reliable, you may miss to evaluate a point you should have evaluated. But that's like inherent. I mean, typically the computation of sharp error bounds is like more expensive than solving the actual problem, right? So the question is how much effort you want to place into this part of the method. We did indeed. I mean, what we sometimes do for models. I mean, for case. Sorry. For cases like this, I mean, we actually do this, right? I mean, 9 days is still something you would do. If this becomes month, you may even not actually do this, right? Because you cannot afford it or it's ridiculous. But for these kind of cases, we did it, and you may have, and I think in this case it was actually 0, but you may have 1 or 2 wrongly classified ones. But this, I mean, should not change much also in the total probabilities you get, right? So in that sense, I think you can even survive if you have like 1 or 2 samples wrongly characterized. Yeah, very welcome. Please.
What was the dimension of this problem of the input domain?
I think in this case it was. I think indeed these 4. Oh no, one is double. So it was 4 parameters. But we did also bigger ones. But that was 4. So it's still medium sized. So that's your question. I also would agree. I mean, the implicit question is maybe how does it scale? I don't know.
Yeah.
Okay. By the way,
How much does it depend on the select kernel parameter?
Yes. So I mean, online crowd, 2 questions. I mean, how does it scale for many parameters, and how does it depend on the kernel choice? So in this case, we could be quite sure that this function is very smooth. So I think we took a Matern kernel or squared exponential. I would have to check exactly which one of we took. Yes. Yes, but we used hybrid. No, not hybrid. Hyperparameter fitting approach. So I think we used here the toolbox of Julian Becht, which just does the fitting for you. So that means also, indeed, if you add more samples, also the fitting would be redone. I remember we had a lengthy discussion with reviewers regarding the paper, how much these costs are, and I agree. This comes also. This part comes with cost, right? The hyperparameter tuning is a step that may cost a bit, but yeah, and at least in the world that we have in our heads, one evaluation of the function is so much more expensive than fitting these parameters. We don't care essentially. So if that takes up to a minute, it's still typically significantly less than an expensive finite element simulation. So these costs we assume to be nothing essentially. Yeah. So if you in this, I think it should be in this paper, but I can also look it up if it's really interesting. But I mean, we tried typically Matern kernels, and I mean, if you know that the function is sufficiently smooth, Matern or squared exponential, and they tend to work well for us. But again, I mean, this the dependency on those parameters turned out to be smooth. I'm not sure if you have mathematical results to actually prove that. So the question is, right, if I change that parameter, does my quantity of interest complex differentiably change? If that's the case, then you are in a very nice world, and actually all that should be beautifully. If this is less smooth, then yeah, there may become issues with the kernels.
Compare this with the learning function?
No. I mean, I don't think we did that. No, we did really. We just used those Kriging approaches and the polynomial one. So we didn't do that one. Sorry.
You select a sample which maximizes the ratio between standard deviation and the mean value. And the mean value, if your boundary is 0 between the failure and non-failure, then maximization of this number would be
Yes. So I'm pretty sure that these things should be also discussed in this paper. So they compared different kernels and different also selection strategies to add additional points, which is also then in some sense related to batching. So there were 2 papers that I looked up. I mean, there's one. The question is in which order you should evaluate those points, and then there's a second question: how to compromise on that to also increase parallelization. Right? These 2 things are in some sense contradicting goals, right? Because the learning is by nature it's sequential, but so you cannot parallelize that. So in this, then you have different ways to choose those points. Yes. If I recall correctly, that paper, there are 5 different ways that they to compare and discuss. They performed all reasonably well, let's say. So in that sense, if I remember correctly, there was not really a loser, also not so much. I mean, there was, I think one method was better, but also not such a clear winner on the other hand. All right. Okay. Second case study that I'd like to discuss. As I said before, I will do the eccentricity study. and I will try to do the physics quite shortly. So the topic is accelerator physics. We did simulations for pieces of an accelerator. So this picture corresponds to CERN. This exact study was not for CERN. It was for the accelerator in Hamburg called DESY, but it has somewhat the same ingredients. And they have magnets, like big electromagnets, to keep particles on track. And they have so-called cavities, so resonating cavities. These are electromagnetic devices who create an oscillating electromagnetic field, which gives the particles you want to accelerate always a push, let's say. And then the particles are shot on the target, and then physicists are happy and make experiments, right? That's the story in short. That what happens in particle colliders. And these cavities look, for example, like this. So that's the so-called Tesla cavity. That's the one that is also used in Hamburg, and that's the one we simulated. That's another picture. There should be a movie, but I'm afraid on this machine it will not work. But just very quickly, so the particles are coming from the left to the right, for example. The electromagnetic field denoted here by those arrows is oscillating, so it's changing. And so the idea is that the particle, and that's very unfortunate. Okay, let my particle come from the right. Okay, then my story is easier. So the particle comes from the right, then it sees an electromagnetic field that gives it a push. So and while now this particle is traveling through that cell, the field has oscillated and changed direction. So once it arrives here, this one also points into that direction, and that's how it gets a push. Okay, that's like the very principle, the principal system. And those things are super sensitive, super expensive, and super sensitive. So it's like 100,000 euros per piece. So accelerator labs do really a lot of effort in measuring all the data regarding sizes, mismatches, and so on. And that's why it was a super attractive target for us to do uncertainty quantification studies, because you finally have measurement data available, and they have a database where you need to get access, but you can apply for it, and then you can really also access all that data, even if you are not a scientist on site. Yeah, and then as I said, it's very sensitive, so it's like a musical instrument, right? It needs to be tuned to the precise frequency, because if that particle is not, if the speed of traveling of the particle is not perfectly aligned to the frequency of changing electromagnetic field, it will get, it will break, right? It will break down, and it will be slowed down once it changes from one set to another. Okay, and it does work. Okay, look there, and it comes from the left. So I didn't expect that this actually works. Yeah, I think that's clear. So we did several things regarding this, because we had, there was interest at DESY to understand this more deeply, and it was for us very attractive because we had so much measurement data available. So that's part of the production process, which we actually also tried to mimic on a computer. You remember we discussed how to get the input uncertainties, and I said, yeah, either you choose measurements, or you really try to model the process of production, and that's somehow what we tried here. So this is the final cavity, and it's created by so-called by so-called belts, right? And then dump belts. So they are then welded to each other, and then this shape is created. And we really tried to mimic this process. So these metal pieces, they are created by a deep drawing process. So that's like a simple picture illustrating that. And then those guys are connected to each other. And then the whole production process works like this. So this is done. It's welded to each other. First step. Then there are many different steps. So there's a trimming process. Then there's a selection.
Enfin, j'avais les données mobiles quand même, je sais pas, mais peut-être que...
I think that, is that a question, or can you mute your mic, please?
Oui, mais comme j'avais quand même les données mobiles activées, je pensais qu'il n'y avait pas le Wi-Fi.
Oui, mais il capte le Wi-Fi.
Can you please mute your mic?
Ouais.
Il faut désactiver le Wi-Fi.
Ouais, mais je dois désactiver. Oui, parce qu'à mon avis, Kevin l'a coupé. J'avais pas pensé. En fait...
Okay. Didn't sound like a question, didn't it? So. Okay, but I'm lost. No, my screen is lost. No, it's there. Yep. Okay. So then, there's the production of these dumbbells, and they are trimmed, they are selected and sorted. Then there's a welding process. Then they do some chemical treatment of the surfaces. Then the stuff is tuned. Then some additional preparation steps, and then you end up with the cavity. And we try to make really a simulation of all these steps. such that you understand from the uncertainties here how they propagate toward there. And I want to give, and then in the end, these kind of quantities of interest, which are called modes, I will not go into much detail, they inherit somehow uncertainties regarding to that production process. I will skip the equations, okay? So this is maybe I will just mention that this was challenging because it's an eigenvalue problem. So it's not a source problem, but an eigenvalue problem. And the challenge is that I would say that eigenvalue problems are even a bit more difficult to solve than source problems. So we had to overcome some difficulties over there. Okay, so in the end, we had data. This is indeed not simulated data, but this is what actually measured data on the eccentricities of these 9 cells. So we did also simulations to come up with this, but now this is really taken from the database of DESY, and it's of course it's magnified. Yes, of course. This thing is 1 meter in length, and these deviations are in the millimeter range. And you see here, if I look, let's say from what is it in that direction into the cavity, you see there that the 9 cells have centers which are slightly misaligned, okay, just because of the production process. And then we got the measurements, and that's now where I want to head towards Caron-Loew expansion, which I mentioned as a very important technique for modeling uncertainties. So you see here that we have the X and Y positions of the 9 different cell centers. That gives us 18, if I'm not, 2 times 9 should be 18. And 3 times 6 is also 18. Yes, it works. So it's always the X and Y component of each of these cell centers. And we also did statistical tests, but also by visually inspecting, I think we can agree that this looks quite normally distributed, yes. But this picture is not sufficient, right? Because it does not tell you what happens to that cell if that cell moves up and down. So the correlation story is essentially missing here. But since we had all these measurement data, so we could essentially find out the point that leads to this bar somehow, where is it located in all the others, right? And this tells us how the correlation works. And what we did was exactly PCA, if you like, or discrete Caron-Loew expansion. So we put the measurements and into the correlation matrix. We did an eigenvalue decomposition, and we did this truncation that I explained. So in this case, those 18 parameters could be reduced to just 7 parameters. And I hope that this picture maybe now finally gives you an idea. So by the way, we got discrete data, right, for these cells. What we then did, we fitted a spline through that data, because if you want to deform a geometry, we need also the information what happens in between, yes? So that's the difference. We didn't really get fully resolved spatial data, but only discrete. But then this could be one of those modes, one of those 7 modes that explains a large part of all possible variations. And then the uncertainty quantification will be just as in a 7-dimensional parametric space containing those deformation modes. Okay, does that make sense? So that should be like a very practical example how the Caron-Loew expansion is an interesting first step before you do uncertainty quantification to model that, to reduce dimension and to have the independence of the variables. Okay, and then we did stochastic collocation. We tried different grids. One can do also Monte Carlo, and now the story is basically exactly what I have told you. There was one tricky thing, so maybe one of you is also interested in eigenvalue problems. With eigenvalue problems, you have the issue that if you modify the geometry, the eigenvalues will change, yes? So that's maybe the deformation that you do, and that's the eigenvalue. But it may be that eigenvalues cross, right? Because you have several of them and they change and you don't know how they change. And then if you want to do uncertainty quantification, typically eigenvalue solvers give you the eigenvalues just sorted by size. That's how they return them. And this is not necessarily, so the first one is not necessarily the one you want to follow, right? Because at that point, maybe this was the smallest eigenvalue. So we were interested in doing uncertainty quantification maybe for this guy. This is maybe then the second largest. Then we do deformation, and we cannot, or we should not follow this one, but we should follow after the deformation this one. So what that requires us to do was a so-called tracking procedure. So we basically didn't modify the geometry in a big step, but we always on very small instances changed it and then tracked back this. Actually, we did this, it took some time, but also we did this with model auto reduction. So that's a bit connected to this bifurcation story that Professor Rotzer told you, right? That where you have to follow somehow the deformation to not. I think he had bifurcations, right? It's not really in bifurcation, but it's not so different, right? You have to choose which branch you have to follow. Okay, but that's a specific thing for eigenvalue problems, which are not so much covered, I would say, in the uncertainty quantification literature compared to conventional PDE source problems. Yeah, and that's what we did, right? So you compute one sample, and from that sample, then you vary, and you can do that by a homotopy. So you basically make a linear combination of those two values, and then you follow this path, which makes things even more expensive. Okay, we did that with splines because we thought that's a very powerful technology because the shape is very important. It's very circular, right? So you can really make use of NURBS for the geometry representation. Okay, this is just a summary of the workflow. I think I can skip that. Yes, and here we see the variance, or this more precisely the standard deviation for those fundamental modes. I mean, for the first 9 ones, which are the interesting ones. Yeah, and there we could see how large the variation is. And in the end, we could conclude that the offset we see because of the cell centers is, well, unfortunately, not a big thing. So that was interesting for DESY to understand, because if they control their production processes, they know that this is not a big issue, right? So they expected that, but we're really 100% sure. So they wanted the study to be sure what are the parameters to look out for. Yes, what are the relevant parameters? Yes, and actually, because it's the deviation that you would get from the deviations is even much smaller. So we needed actually to magnify these deformations by 50 times just to be able to quantify this error, because it was so small. The eigenvalue solver needed so much accuracy, but it was still good enough. I mean, we could estimate that the true variations are then only in the range of hertz eventually. Okay, so that was, I think, a nice example, I hope, because we had discussions on the Caron-Löw expansion that maybe gives you some visual explanation how this works. Shall we discuss Caron-Löw expansions? Other questions regarding Caron-Löw expansion or the modeling of things like that? Any comments, maybe? If not, I told you, I will not discuss the variance-based sensitivity analysis, but I like to do a very brief overview regarding robust optimization. No. Maybe just yeah, okay. Sorry, the title is wrong on the slide. That's why I was confused. No, it's the right lecture, but the wrong title. Okay. For the people that do optimization, they will probably also realize many things they know. This is my agenda. I think I can do some things here also quite fast. I have, in the end, just selected 3 optimization methods because I think they are good candidates because they belong to 3 different classes of methods and they are all popular classes. But I mean, yeah, I just give you 3 ideas that you may already had before, but just that you are aware of what kind of classes of methods are available if you do not know it already. Okay, my fault. I don't know how it's my fault, but it seems to be my fault. Okay. Right, so robust optimization. I already started in the very first lecture to give some intuition, right? So that would be a classical optimization problem that you have. And the point is that in many cases, it doesn't really make sense to do this because you have to account for uncertainties in the inputs or in production process or whatsoever. I will try to keep the same notation I did before, right, with my deterministic parameters, my randomness, and my range parameter. And especially in the beginning of this, I follow this paper, which I can really warmly recommend. It's a nice overview over robust optimization. It's not super recent, but I think it has all the interesting ingredients and does a good way to explain things. So if I recall correctly, these people are from Honda. And I think Professor Zenthoff even has connections to TU Darmstadt, but that's not the reason why I'm recommending this paper. Yeah, so I think I told that story already, right? So what is the relevance of an optimum? So it's probably none, right? Because we know that our simulation models are not be exact. So what is the point of computing an optimum up to the power of 10 to the minus 8? There is no reason. The model is probably less good. Secondly, the optimum that we have computed is probably not as precisely manufacturable. So there's also another reason it doesn't make sense to compute with high precision one specific optimum. Furthermore, conventionally, but this can be overcome to some extent. So this is a point from this paper. No, I think the third point is also from the Zenthoff paper. They argue that the problem is static, and I agree. Typically, you optimize things at the design stage, at design parameters. But I think this is not intrinsic a problem, because you somehow can, of course, account in the optimization problem also for aging, for example. Often it's not done, but theoretically this could be incorporated. But generally, I mean, yes, most people, if they optimize, they don't consider aging. So most probably the optimum that you compute is only true at the very beginning of the life cycle of a product. Yeah, and then there's another point that life cycle costs are typically not included. So this is rather not so much about the static behavior. This point is rather that if you have specific designs, they may need very high maintenance. So I think I told you about some optimization problem we did also for a particle accelerator lab where we optimized pole shoes. So don't worry what is a pole shoe. Anyway, it was a shape optimization problem, and we came up with an optimum that looked like this. And they were very unhappy. I mean, they didn't told us in the beginning about this, but they were very unhappy about that kink because they said, well, dust is collected in there. That's bad. And so that was the reason they didn't like our design, because of dust, which made totally sense. And we could have included this in our optimization, but we didn't. But the point is, so they rejected that because of maintenance, right? Because it would be cleaned. And then this might have been radiating. Cleaning is also very difficult. So, but anyway, my point is, depending on the design you choose, you may increase some costs in the lifetime of a product, which are not obvious to you. And that's also another reason why sometimes a specific optimum might not be so reasonable. I like quite a lot that from that paper, that statement. So optimization is actually just the opposite of robustness. And I think that's, I mean, it's a bit catchy. It's a bit wrong, but also a bit true, right? So I think it's nice to keep that in mind. And this is just a picture to visualize that, right? If you have a function, you want to find the minimum, and you have those two options. I mean, it doesn't need much fantasy that this is the better. I mean, I'm very well aware that a better optimum is a very strange expression, but in this case, that this is the better choice. Let's put it like that. Agreed, right? Because if you have variation in this parameter x, so this remains good, right? But that will fail immediately, quite badly. So this whole story of robust optimization goes back to Taguchi's robust design methodology. It's one of he's considered like the father of robust design. He distinguished between 3 steps of design: system design, parameter design, and tolerance design. I don't like that too much. I think that's so it's easy to say because we are like a few years later, and it's also maybe not, you know, you shouldn't criticize the father of robust design most probably, but I think this distinction between the different design stages is nowadays even a problem because it's done. So I think that if you could do more optimization in the full parameter space earlier in the design process, I think we could get a better product. To some extent, this has also drawbacks. And additionally, the point that parameter design and tolerance design essentially only differs in granularity. So I also don't think that this is a big difference. But anyway, that was the concept that he originally came up with. So and he proposed in the optimization to account for performance variations due to noise. So that was like the topic at the time. So uncertainties he rather perceived as noise, and he distinguished, or we distinguished then here again into these control parameters, right? And they have noise factors, and then there may be additional production tolerances. So this can be split, as I already advertised in the rest of the talk. So there may be different sources of uncertainty. They may be aleatoric or epistemic, but in the end, you can express this always in a shape like this, right? Where you have your, let's say, deterministic mean parameters and the randomness. So Taguchi at the time used the mean square deviation as a concept, and I mean, this rings a bell, right? That's essentially the variance that we introduced from the stochastic point of view. But this was at that point also not yet put into the statistics context as it is these days. So he defined this signal to noise ratio. I mean, I also don't bother too much. I would say that's rather heuristic choice, but that's how he did it. And at that time, he also didn't really propose an automated optimization procedure to maximize this, but essentially he took a lattice and evaluated this on this lattice. So this is, yeah, I mean, I think also that's a very nice quote from that paper. So it states that the Taguchi approach violates a fundamental tenet of numerical optimization. One should avoid doing too much work until one nears a solution, right? So in this approach, a good optimizer will go quickly to in the neighborhood of the optimum and then stay there and then improve on in this method. With the grid, of course, does not do this. So, but nonetheless, I think it's relevant to have an idea. And indeed, I mean, this kind of course of dimensionality with these learning methods, this could have been significantly improved, right? If you would have done this lattice and maybe done that, a learning method, whatever you choose, this whole method gets already way more attractive. And less expensive. So let's put it less bold. So not AI, but surrogate modeling in general could have helped to break that or at least to mitigate to some extent the curse of dimensionality. All right. So this was like a brief historic overview. Then I like to discuss 3 robustness concepts before I then show you some methods. So that was our setting, right? We had one or several KPIs that I named Y, Y1, Y2, whatsoever. They correspond to function evaluations of our costly PDE. And then I think it's so these uncertainties can pop up at different situations, right? So we can have, and this is a categorization also from also mentioned in the Senthoff paper, but it comes originally from this one, where they distinguish different types of uncertainty. So we have the ones that are more due to changing conditions. Yes, that's what they call the type 1. They can be directly modeled by those Xi's. Then they have production tolerances, which they call type 2 effects. They actually affect X, or they would affect D, but or this position of our function f. But since we can essentially, I mean, if we have a randomness, for example, a normal distributed variable, I already explained that at some point, right? Then D can be perceived as the mean, and then this Xi can be just an uncertainty, a normally distributed variable around 0. So then we can split this Xi from that D, and we can essentially define a new function that again has this shape. So I think this shape remains still valid, right? So either the uncertainties pop up separately, or you can somehow redefine your function f, and then it's also perceivable in that shape. Then you may have output uncertainties, which come maybe as an additive term to the evaluation, but again, this can be put together and perceived as one function f that depends on D and Xi. And then there's so-called feasibility uncertainties that are not really attacking my function f, but if you remember, and I go back to, I think, the first slide today, in this part, so uncertainties may also appear in G and H, of course. This is a bit different, right? Because, I mean, just to make that clear, so G and H are somehow defining the space in which you are looking for the optimum, right? And this is like the function that defines the optimum. So it's like it's really a different kind of nature of uncertainty. Okay, so that can be distinguished, and again, I think it's relevant to have this have the ideas, but nonetheless, from the very practical point of view, this can be all brought into that form. That's, I think, the main message from that slide. And then there are several ways, and I think that it's reasonable to distinguish between these 3 cases. So you can deal with uncertainties in a deterministic way, you can deal with them in a probabilistic way, and then there's also a possibilistic way, which I will not discuss. So that's related to fuzzy measures, and there's a lot of theory behind that, and this is one paper from that branch, let's say, of ideas. I will not go into that, so I will discuss those 2. This is like mainly fitting to the main scope we did before, but since this has also a lot of relevance, I like also to quickly discuss what are deterministic possibilities to treat it. We start with that. So then the first idea that people have, and that goes back to ideas of, well, I don't know if it goes back to Benthal, but for sure in the book of Benthal, this is discussed a lot. So the idea is we don't optimize my original function f, but we define a neighborhood around that function f, so noted here by this epsilon, and then we look in that neighborhood. So we want for the supremum, or let's say the maximum. So it's supremum because I'm not sure that this set is open or closed. That's why I put the supremum. But anyway, let's say maximum to make our lives easier, and we want to minimize that function. Then we minimize that function, but choose xi's or look at all xi's in the neighborhood of that x. Yes, and that's then our minimum. That's the idea. And obviously, if we choose epsilon to, if we move it towards 0, then this recovers obviously the original function. So that seems to be like a legit generalization. But that leaves us with the min-max problem, right? We have to minimize and maximize at the same time. And this is, of course, very costly. I've drawn here several examples. So this was my original function in black. That's the one here. And then I modified according to epsilon the goal function that an optimizer would see, and then I colored it. And you quite naturally see that if I make my epsilon region larger and larger and larger, this minimum on the right is not affected by it, because if I look in the neighborhood of this x here, I don't see much increase in my goal function, so they all more or less stay here at the same value. But since here I have this linear growth, I see that if I increase my epsilon, so meaning I look for the minimum in the increasing interval, I increase the value. So, but the nice thing about this is, or the easy thing is that this can be, in the simple case at least, can be then just put into an optimizer, right? Then this goal function needs to be optimized, and then hopefully it will find this guy. Of course, this is in multi-dimensions not so easy. You may not have the black curve given analytically, and you may not be able to do this simple mathematics to compute these green additional lines. Okay, but I think what we have achieved, which is nice, that the engineering intuition that this one is bad and this one is good can now be characterized, right? Now we have a tool to make that, to work with this. Okay, then we see also that, I think that's a very interesting thing. So but it's also not surprising that the x, or the minimum may move, right? You see that depending on the interval, and the example, that's an example where that is constructed exactly like this. So this branch is linear, and this is, I think it's a square root, if I recall correctly. And you see that because after you increase the interval beyond 1, you see that it's different which function is somehow leading, right? So then we have a tendency that in the beginning we move to the left because this one has less curvature. So it's more attractive to go towards there, and then at some point it skips the other way around. Yes, and that's also what we see here. And particularly in this function, I think it's also very nice to see that we are in the lucky case that if we have this curve, which corresponds to epsilon equals 1, that we recover the same, let's say, x value as we would have had for the same function. And this is also visualized here. So you see that if we increase the robustness, if you like, then we see a change in the x value we get. And we see, well, it starts at 0, but then it moves, and then it crosses 0 again, and it moves again further. Okay, I mentioned already that I will also quickly discuss Pareto. The point is, I will only discuss Pareto in the context that you have now obviously conflicting goals, right? You want to minimize a function, but at the same time, you want to increase robustness. And these are conflicting goals, and this can be treated in a Pareto setting. So Pareto fronts are I mean, the Pareto front in this case would be this line. And this Pareto front somehow corresponds to a line on which points lie, which cannot be improved further without, let's say, sacrificing the other goal. And then you have, well, the range of, or the parameter space of points that are infeasible, that you just cannot realize. Then you have all the, let's say, inefficient solutions. And then these are the ones that are, let's say, the best you can do. And then a designer is supposed to choose one point on this Pareto front. In this particular case, I think the choice would have been easy because this point is really a sweet spot, yes? So, but that's because this function was constructed very specifically. But generally, of course, it's a more tough decision what point to choose. But nonetheless, I want to make clear that generally, this is a compromise, and you may have to make a choice what you actually want to achieve. Yes, okay. Quick summary on that. So I think it's very clear that this is costly compute because you have a bi-level optimization problem. What I did not discuss, but what is also a very common approach, is to consider not the function value, but the maximal derivative. So you optimize something like that, where you have the goal function, then you add some scaling, I think some also call it risk-aware factor, and then you maximize in the neighborhood the derivative. This is, I think, a much nicer approach because if, it does not just look, at the interval, but it also somehow accounts the sensitivity, takes into account the sensitivity of the function a bit better. But this is just a different formulation, and but that fits into the deterministic part. But it's like, it's different. Typically, you don't do this really with the min-max problem, but you substitute this f prime or this or the f, if you use the original formulation, by some linear or quadratic approximation. Because it's, and then you can compute, let's say, the max or min or anything somehow analytically or based on closed form reasoning. Because really doing this would be very costly. So we never did this, and I think rarely anyone is really doing this min-max with two nested optimization loops. The one drawback is that robust optimization is somehow often regarded as too conservative, right? Because you are really taking the max value and going back to my, I don't know what image, maybe to that image. So if you have a classical production process, you may assume, for example, that you have a normal distribution. So this variation from 3.5 to 4.5 around 4 may be weighted by a Gaussian curve. So you expect that these points are significantly more relevant. So then the question is, do we really care about these very rare cases? But that really depends, again, on your application, right? If you can afford, let's say, a few outliers, or if you really want that every single device fulfills the property you need to fulfill. That may be also a question, how expensive is the device? What are the mass production you are in, et cetera, et cetera. Okay. Yeah, and you have seen that choosing this epsilon is, of course, also tricky and reduces performance. Yeah, but I think it's obvious. So we did actually this, and we did also the another approach I will discuss now, the stochastic approach. The stochastic approach is somehow more precise because it gives you really like precise information how rarely things can happen in this kind of optima you get. But since sampling is involved, this is potentially very, very expensive. So doing this robust optimization, if you have derivatives available, so let's say you have up to 3 derivatives of your function f, then this is like super efficient. If you have 3 derivatives, if I'm not doing any mistake now, I mean, if you do gradient-based optimization of this, you will need at least 1 additional derivative of the goal function, yes? Maybe even 2. Okay, let's say we need 1. And then we need at least, and then we have 1 derivative over there. So we need at least, okay, well, I was wrong. We need at least 2 derivatives, right? To be able to make a gradient-based optimization of this expression. If you have those, then you can do a proper approximation of this. Then you can build like a linear or quadratic approximation of this and just optimize. And this is hardly more expensive than doing the original problem if you have those derivatives. Okay. Then we come to what Bayer and Senthoff called measures of robustness or momentum measures of robustness. And this essentially now connects, I mean, you all know all this. It connects back to the moments, the stochastic moments I introduced. So now you can define your goal function to be any moment that we had, right? And quite naturally, the most interesting ones are most probably the expected value and the variance. And then you can do combinations of those and minimize the expected value multiplied or plus and some risk-aware factor, and then the variance. And this is then the goal function you want to do. So here we have a closed form solution. So we want to minimize this specific goal function, which is again from the Senthoff paper, where they constructed this because it has some nice properties, and you can indeed compute the 2 moments exactly, right, on a piece of paper. So which is not true in general, right? So this needs sampling in general. That's why this is expensive. If you can do it by hand, okay, it's nice for explaining things, but it's not very realistic. So this would be, just getting here is in practice very expensive. Okay, anyway, here it's cheap, and we can just compute it, and these are the results. And now we want to minimize this. And they propose, I think, a very natural linear combination, right? They introduced one parameter beta, where they do a weighting of the expected value and the variance. As usual in optimization, right? You can do this, which is, I don't know, mathematically quite nice, but essentially, since, well, you could even drop this guy over the guy over there, because if you optimize this goal function or 5 times that goal function, doesn't matter. So essentially, you need just one risk awareness parameter. Okay. Yes, and by the way, we talked about conflicting goals and Pareto fronts. So this kind of weighted sum approach, I wanted to warn you, only works, you only recover the full Pareto front by this. But if you vary beta, right? You could think, well, I get the Pareto front, right? I get all the possible variations, so I can, if I choose, now what do I have to choose? If I choose beta to be 1, then this guy vanishes, I only optimize the variance. And if I choose, and I forgot it immediately, the other case, I get the expected value, and you would expect that you return the Pareto front. But unfortunately, this is not the case. It's only the case if the Pareto front is convex. So this is not a general solution. So it's not, I mean, very often this is done because it's much cheaper than Pareto-based optimization, but it's not the same exactly. Yes, but in this case, the Pareto front is convex, and we see this. So we can vary beta, and if you have beta equals 1, we end up here, and if you choose beta to be 0, we optimize somehow the other case. I created that plot similar to the other one. So if we go up or if we go to the right, let's say we decrease the goodness of our solution. So that decreases going in that direction, the robustness, and this decreases, that makes our performance worse somehow. And then you can choose some point on that Pareto front where you want to, choose where you are. And in this case, even if you would have done multi-objective optimization, indeed you would have gotten the same kind of plot, right? And then this approach may have been cheaper, right? Because here you just have to evaluate for different, you have to optimize this function just for varying beta, and that tends to be a simpler approach than doing the multi-objective case. Yes, please. Yes, definitely. I think I will even have a slide on that. No, definitely. So in many cases, you may not need to do this because, I mean, this is really if you have no clue in the end where you want to be, where you really want to create that Pareto front. But very often, and that's also a way to make your optimization problem less expensive, you may just specify one of those two as an equality or inequality constraint, and then you have you just reduce the number of objectives. Yes, no, that's definitely a thing we also do. Yes, I agree. Yeah. And that's exactly this what I just explained, isn't it? Yeah, I knew I had a slide on that. Okay, so this was the multi-objective case where you really have two conflicting goals that you may want to minimize. Then we discussed this weighted sum approach, and indeed, often it is not necessary to do this, and you can either minimize the variance and ask for some expected value as a constraint, or vice versa. Yes, okay, that's just the mathematical expression for that. Yeah, so I said before that's expensive. It's typically more expensive than the robust optimization I explained before. Typically, I mean, so what is robust optimization, robust regularization? Typically, at least in the mathematical literature, refers to the deterministic approach, and the stochastic one is often also called the stochastic approach. But then be aware that this is very easily to be confused with stochastic optimizers, right? So stochastic optimizers are the method to optimize, and this is like the stochastic formulation of the problem. So that's also maybe sometimes confusing. Yeah, you could do that with Monte Carlo, obviously. You can do quadrature-based methods. We have done in challenging applications where you wanted to have this stochastic approach very cheaply, and I've seen also many other colleagues do that. We do this kind of Stroud-based quadrature formulas, which gives you at least some idea on the variance and expected value. And depending on your, I mean, I said it scales in the number of dimensions. So let's suppose you have 10 random parameters, then you need to evaluate 1 times the goal function. With a Stroud formula, you would need 10 times more, right? So that's not too bad. It takes 10 times longer, so that's a lot, but it's not crazily exploding, right? Okay, and then of course you can do you can use learning methods. And as I said before, if you you may have to be careful, or you may want to choose carefully your optimization function if whether you are interested in the mean or in the tails of your distribution. So in this setting, this is really you put your focus on the mean of the distribution, right? Think about the Gaussian. So here I just look at the mean and the variance. So I'm not really looking what is the probability way down that path, right? And this formulation is really good if you're interested, let's say, in a big mass production and you are not caring too much about rare cases that might violate something. This case, where you want to also look at very rare cases, can also be done, but then you have to work with probabilistic threshold measures. And this is related to the yield we just explained. So again, we regard x now as a random variable, or more precisely, this xi. This is just the f function we had before. And now we want to optimize the likeliness of a desired event, meaning the yield, or we want to minimize the probability of an unwanted event. So that's what's written down here. And you see now 4 variants, which are essentially the same thing. It depends whether you want to do a robust minimization or robust maximization. So if you want to do a robust minimization, you want to maximize, and be aware, right? It's a minimization problem you want to solve, but you maximize the probability to be below a threshold. So that would be this case. And then just exploiting the fact that the good case and the bad, the good probability and the bad probability are just rated by 1 minus, and the minus is the interesting part. You can just equivalently formulate this as a minimization problem where you in the end optimize the bad case, if you like. And then the robust maximization is essentially the other way around. Again, you maximize the probability, but now you want to make that function bigger than some minimum, or the minimum value, your performance feature specification, or you have here the case where you minimize then and just flipped that greater sign. Okay, and the whole yield fits into that scope. And this is really a thing. I mean, if you evaluate that probability properly, that's where you are rather looking at the tails, for example, of your distribution. I mean, now depending, of course, how you choose this f, but this is typically done in the case for failures or yield, where you're not just interested in the center, let's say. Okay, again, there's no closed form solution available. I would say that this tends to be even more expensive than the optimization of expected and variances, because you cannot just deal with normal quadrature anymore. That goes back to the statement I made before, where Dongbing Xu explained in one of his papers that these surrogate models may not work well for these kind of situations. And this is, I think, exactly from the same paper again. That's the example that they do that I think it's very intuitive and very nice. So let's suppose a very, very simple case. So we have a goal function that is just 0. Okay, very nice, easy case. And our performance specific, I don't get that word today, I'm sorry. Performance feature specification is that we want that this function is greater or equal 0, which is very easily actually achieved, right? And it's almost surely that this is the case. But now I define the following approximation, like that could be my surrogate model, which of course is totally not necessary in a simple case like this, but I could have defined a surrogate model, and actually it's a good, not such a bad surrogate model, right? I define a function fn, which is minus, and the minus is the crucial part of this construction, 1 over n. And this obviously converges for n towards infinity to the function I actually want to approximate, right? But essentially, in all cases, this gives me the wrong probability. I mean, for all finite n, this will, the result of this function will be negative. I want to have a positive function, so it will be always a wrong result. So I will always characterize things exactly the opposite. And this construction, I mean, I agree, it's a bit pathologic, I think is the word you say, but it shows the problem that you have there. And that's why it's necessary to do this kind of hybrid approaches. All right. I have 20 minutes left, roughly, yes. Okay, so then I will do this actually also quite short, because I think most of you are aware. So first of all, typically, but that's I think clear for engineers, maybe less clear for mathematicians, it's not a good idea to re-implement an optimization method, right? There are very good libraries available. And for example, I just picked one. I mean, there are so many, right? I just picked one that is, I think, quite famous, that is NLOpt. and it contains a lot of very nice optimization methods. But I'm not by no means I'm saying that you need to use this, right? But it's one good choice, I would say. And you see, it contains a lot of these methods, and it contains so many methods because it's not so easy to choose a proper optimization algorithm. Because in some cases, one of those is always the best choice. So there's no silver bullet. That's what I want to say. And I will discuss now essentially just a small selection of this. So I think I will start with SLSQP and BobbyQA. I will explain them in one go, let's say. And then, and I'm sorry, I cheated. So it's not so many. I think this should be one line. That's COBBYLA, which is like the brother algorithm to BobbyQA. But anyway, this is, I'll not go down that route because otherwise I'm just explaining methods here, and also I don't know all of them, to be honest. So this picture I think is also a very nice one. You may be aware that there are like flow charts, right? That can help you if you start optimizing a problem, and you can just go through flow charts like this and check, is my function affine? Do I have a quadratic function? Is it generally nonlinear? Then do I know whether it's convex or not? Do I have constraints? Yes or no? Do I have linear constraints? Yes or no, right? Can I eliminate the constraints? Yes or no? And then you follow that path, and flowcharts like this, and there exist many like this, so I just picked one that was nicely available. They can help you to narrow down, to find the best algorithm for your problem, okay? So that sense, I can't give any recommendations on that. Yeah, I told you I like to just roughly talk about 3 classes, just to put everything into scope. So I think if there are derivatives available, then this SQP method is very attractive. If there are no derivatives available, there's this method called BobbyQA, which works roughly the same as SQP, but it trades between derivatives and function evaluation. So we are looking for that optimum, and I mean, this word quadratic in the name already gives you the idea that you will do piece or iteratively quadratic approximations. And I really like, I mean, that's also one reason I put that here. So in some sense, you know, optimization algorithms since decades use polynomial interpolation or approximation techniques inside to learn, right? I mean, nobody calls that learning somehow, but this idea is already present in there. So it will, you know, again and again do a quadratic approximation. And why? Yeah, because if you have a quadratic function, well, determining the minimum is, even in high dimensions, is almost for free. And then this works also similarly like a Newton method would work. And then you will approximate eventually the minimum that you are looking for. And now there are different variants, right? So the construction of this parabola, that you can do this by function values. And if you have additional derivative information here, then you can, and this is possibly even if it's cheaply available, then this is a very effective method. And this essentially comes back to what people call sequential quadratic programming, as the SQP method. If you do not have derivatives available, what you can do is finite differences. To our experience, this does not, I mean, if you have the derivatives, that's great, just go for it. If you need to find differences, this approach is not always so super efficient. Then more attractive is BobbyQA. And I also know that in Steffi's group, this is, or used to be one of your favorites. So this does the following trick. So instead of evaluating this point and maybe 1 or 2 derivatives, this method will just evaluate more function evaluations and then force the polynomial to go through this function evaluation. So you somehow trade in derivatives to more evaluations of functions, very roughly speaking. Then you can do, another option is that you can do regression. And that's a method that also we looked into, especially we looked into a method where you do regression if you have some derivatives available. Because for the yield, I will come back to that in a minute, you have some derivative informations available, so it's very attractive. It's noisy, but you have derivative informations, and then a regression setting might be very interesting. The drawback is that these methods, for sure, BobbyQA, if I'm not mistaken, only works with linear constraints. That's one of the drawbacks. Okay, so the original, and these are just the references, but as I mentioned, most of these algorithms are somewhere implemented already for you. So BobbyQA, it's from Powell. Then there is a method, and I think that comes from this paper, which is called PyBobbyQA. That's actually the implementation we used. And then we extended PyBobbyQA to do regression with some derivative information, which was very helpful for some project, and I will show that later. Then there's a class of Bayesian optimization that we do not use too much in my group, but I'm not saying that it's bad. It's just that we never really fall in love with it, which is indeed based on Gaussian processes. We discussed that already. I think there was a question yesterday on that. Yes, it's essentially based on Gaussian processes with a specific clever ideas. So you are not, let's say, just minimizing the mean that you get, but additionally, you have this kind of trade-off between exploitation and exploration. So this method will also invest somehow additional function evaluations where you have a high degree of uncertainty in the function, because there might be another minimum or maximum hidden, right? Because you have not explored that part of the space. That's why this is interesting. But of course, this may be wasted, right? Because you are not sure that there is something. So that's why there is a trade-off between exploitation and exploration. And there are then different variants how you choose this, but that's your your functions essentially, which give you the information where to add points, and then you do somehow in the end a normal optimization on that response surface. That's the idea of Bayesian optimization. And then there's a class of genetic algorithms. Also there is like a vast amount of literature. Also this, at least in my group, we have never created new algorithms of that type. We have used libraries. This is really very, very powerful. I said in the very beginning that I thought these methods are somehow, from an algorithmic point of view, boring. I don't know. Maybe people disagree who work in that field, but it feels like a brute force approach. But nonetheless, if you have very high dimensional problems, if you're looking for Pareto fronts, they perform very well. There are swarm algorithms, genetic algorithms, so that I would just roughly characterize that class. What we have done there is mainly to create a response surface first, and then we let the swarm or genetic algorithm work on that response surface. This has a significant drawback compared to this approach, because there's, you remember I explained this exploration phase. So if you do this, if you apply this algorithm just to response surface, there is no way to explore anything, right? If you have missed some things in the parameter space, you will never recover it. But nonetheless, if you have many constraints, if you have complex problems, this is very attractive. It just works. And let's give me one more thing what is nice about these genetic algorithms. What we sometimes see is, especially in the finite element world, that you change geometry, and at some point you may have missed a constraint. So that means in the end, if you do it traditionally, not with splines, a measure has to mesh the problem, yes? And the measure may just not succeed because you have, some intersection of some surfaces or whatsoever. So you will, in practice, you will miss a constraint. I mean, that's my claim. You always miss a constraint. You always miss that some parameter may overlap another one, because those dependencies may be complex and nonlinear. You may not be able to understand all these interdependencies, and then your measure will fail, or the simulation will fail, or the matrix of your problem will be so badly conditioned that it just doesn't go through. And that's definitely also a nice thing about these genetic algorithms. They don't care, right? So there's a particle, there's one evaluation that fails. Okay, so what? The other ones still survive. This one will be dropped, and you just can continue. So this makes this also very, very robust. If this happens in a derivative-based deterministic optimization, and this happens maybe very early in your optimization phase. You start, Friday afternoon, you start your simulation, you forgot about one constraint, you come back Monday, and you realize, okay, it did 2 steps, and it stopped because you forgot the constraint, right? This happens, I heard. Rumor goes this can happen. Never to me, of course. Okay. Yeah, that was my quick overview on robust optimization, and just talking about 3 different possible methods. But again, this is vast, so there's way too much to cover. Yep. Okay. So I brought a few case studies. The first one is I think particularly nice because it connects very nicely back to what we explained before. And then in the second part, I will also discuss a case which is exactly of the structure I mentioned at the end. I will do that very quick, by the way, right? I really aim at finishing in time. It's 10 minutes left. Okay, so 5 minutes here, 5 minutes there. Here we indeed did what I just explained, right? We trained a neural network based on data, and then we did a swarm optimization based on that. Okay, in the yield optimization case, and I did all the work already, right? You already know what the yield is, and now the question is where in my parameter space I have to shift, and again I should use a pointer, where I have to shift that mean to make sure that only very few evaluations are outside of my safe domain, right? That's the problem now. And the beautiful thing about, a good thing about the yield is that you can, at least if you are in a setting with normal distributions, you can actually properly derive, well, analytically, you can derive the derivative. And I will not go through that with you in detail because I really have not the time, but the point is you can easily obtain those derivatives. And that was, if you remember, there was a question regarding what happens if you use truncated Gaussians and if you use the proper Gaussian distribution. That's exactly one of the cases where we computed derivatives of our goal function based on the true Gaussian distribution, but for the sampling in the Monte Carlo later we used the truncated one, and that worked like very beautifully. The point is, if you have a distribution with a finite support, you will somehow unavoidably have dependencies, well, in the boundaries of this integral, or alternatively in this characteristic function, so that such that you cannot move somehow that gradient with respect to the mean. You cannot move that behind that one. I'm not sure if I expressed me very well. So you want to compute this derivative regarding with that mean, and this mean will be inside this indicator function if you have, for example, a uniform or a truncated Gaussian. So this derivative cannot be moved here directly and then compute analytically. That's the point why this fails actually. Which is actually, I mean, I'm not saying that this derivative does not exist. I just say it's not easily computable directly. Okay. Yeah, and then the good thing about this is, I mean, if you want to minimize or the failure probability or maximize the yield, now we have derivatives of that, so that's quite attractive because we can use gradient-based solvers. Yeah, the drawback is typically that these deterministic parameters, if they are not affected by stochasticity, are inside of your model evaluation, right? They are not really connected to the yield, but to the model itself. So if you have a solver, let's say an ANSYS solver or whatever black box solver you have, you typically do not have those derivatives available. So, and you will have, if you want to use a gradient-based algorithm, you may have, you need also those, right? So you can either do something else. And that's where the story comes in, right? I told you BobbyQA, for example, is an algorithm that doesn't require derivatives, so that would be nice. But on the other hand, it's a pity if you use BobbyQA, we cannot make use of the derivatives we have at hand. So that means very often, at least in many cases we have seen, you have derivatives of some part of the variables and some you don't. And then there are different choices that you can do. So you can use derivative-free solvers, but then you waste information, or you use gradient-based solvers and you do find differences. Or we do this kind of Hermite BobbyQA I advertised that we developed. Let me also mention, I think I didn't do that when we talked about Gaussian process regression. There is something that is called co-kriging, I think is like the usual word for it, where you can also incorporate additional information in the learning process. So for example, if you have derivative information of your function, the co-kriging can also account for that. That's also one way, you know, if you create a response surface and you have some derivatives, you could feed that, for example, also in the learning process. So but that's not considered here. Yeah, I mean, as I said before, I really like to do this quickly. So yeah, let's look at the example. So that was the problem we had a look already before. So now we have two deterministic parameters and we had some uncertainties. And then we had a look on the computational effort. And maybe not so super surprisingly, even with some finite differences, SQP was in this very simple case quite successful. So the performance of SQP, because it has finite differences, will be significantly worse if you have more dimensions. Let's say for the 5 dimensions that we have here, it was still doing quite well. The original BobbyQA was okayish, I would say, and our Hermite approach was somewhere in the middle. But it gets very interesting for us in the case if you have noisy data. And I didn't talk much about it, but if you do this yield approximation, what we do, and I think it feels very natural, that we increase the number of Monte Carlo samples while we are getting closer to the optimum, right? So in the beginning of the optimization, we only choose very few samples, and then we increase the number of samples just to save computational effort, because we don't need the accuracy maybe at the very beginning, but we need it at the end. But then the drawback is, because you do Monte Carlo sampling, your goal function is not smooth anymore, right? Because if you have only few Monte Carlo samples, you may have big jumps, right, from one to another sampling approach, which means you have a noisy function. And this is an optimization, a topic on its own, how to deal with noisy function evaluations, right? So if you do minimize y of x, and you are confronted with a situation that it comes from the world of measurements, right? If you evaluate that function twice and you get two times different values, this minimization problem becomes harder to do. And this is for simulation-based methods or cases, it's typically not the case, because if you have a simulation code, I mean, it should return the same value, right? If you call it twice, or you have a serious problem somewhere. But in the case of this Monte Carlo sampling, where you really gamble with very coarse evaluations, it might be the case. Similarly, if you do a finite element approach, and you may also have the idea during the optimization to increase the finite element mesh, right? Then you may also end up in situations where your function is, let's say, more noisy, because you have these, let's say, model noise, model uncertainties that come on top. And then in these cases, indeed, I mean, and I think that's also very intuitively clear, then SQP performs really bad. So it takes way more evaluations, and it may even go into a completely wrong direction, right? Because it may see a difference that is just because the number of Monte Carlo samples has changed, right? Because it's very sensitive to these kind of noises. All right. Then there was a second study based on this, where we did, and that really fits nicely now, the last two examples, to the main storyline I did in the beginning. That was together with a software company and automotive industry. We did multi-objective optimization with uncertainties for an electric machine. So we had 12 uncertain parameters, but only 4 deterministic ones. So it was a rather small template. This was mainly, the idea was that this permanent magnet should be minimized, right? This because it's expensive and environmentally polluting, so you want to minimize that and then find the right spot in the rotor where to put it. But then there are uncertainties. For example, I talked about that, the magnetization direction of the magnet may be uncertain. And then this is a robust optimization problem that you want to do. And here we looked, I mean, one constraint was that the average torque that the machine delivers shall be bigger than some bound you gave. And then you can do this as a multi-objective problem. So we had one goal, which is towards the robustness, and the second goal was towards the performance. And performance means now the magnet shall be small, and the magnet in 2D is just given by its width and length, right? So 2 deterministic parameters. That was, and then you have some linear constraints to make sure that things are not intersecting. Yeah, and then you can do the optimization. I think because you are probably not interested in electric machines, I will not discuss this with you. So they all gave, I mean, different reasonable minimization results. But I think the main point I wanted to make is that we could significantly reduce the effort. I mean, that's, I think, the interesting story for you here. So we used this Gaussian process regression learning, and be aware, that might be confusing. We did not use Bayesian optimization, right? We did use, well, either gradient or a swarm algorithm, but we used the Gaussian processes to learn the goal function that then we needed to compute the yield. So we didn't learn the yield, we learned the goal function that is part of the specification. That's different. Theoretically, I mean, you could have also used Bayesian optimization then afterwards, right? That's like somehow orthogonal to each other. Yeah, but I think the good news, and that was because also the company was pleased and is considering to implement that in their own in-house code, is that we could really significantly bring down the evaluation. So the storyline I want to convey is, so with classical Monte Carlo sampling, this is like totally unfeasible, yes? But so you cannot do multi-objective optimization with just sampling. That's way too expensive. But with these kind of learning techniques, you can really significantly reduce the computing time such that that becomes actually feasible. Yes, please. yes. So the question is, by the way, why shouldn't we learn the yield directly? So first of all, I think this is, you can do both, first of all, right? Theoretically. So, and the question is, should you do both? And we thought, but I mean, frankly speaking, we gave it a bit of a thought, and then we decided to not do it. Remember that this is a function. Okay, let me not go back. The function is you have to learn 0 and 1. Right? Because it's 0 if you are in the bad domain, and it's 1 if you're in the good domain. That does not feel like a nice function to learn, right? So I'm not saying that probably methods can do this, but it's not a continuous function that you can easily learn, right? Because it's somehow, yeah, that goes in a different direction. So we thought that that doesn't feel natural, and since once we had the surrogate model from which we then could compute the yield that was very cheaply available, we didn't see the extra advantage of doing that. If you just learn the yield function somehow, you would still have to do for some points the very expensive sampling. So this needs to be done for sure, I think. But I agree with you. One could also do some additional learning on a secondary stage on top. Yes. So the question is, could I extract additional information? I would say yes, because you remember, I mean, I cannot move the board further. So the yield is, it wants some quantity of interest, right? Be smaller than some C. And so we learned essentially this response, right? So I truly believe, I mean, we didn't make use of that, but I truly believe that if you learn those guys, you are more flexible, right? Because from that you can deduce somehow more. If you just learn some of the result of this comparison, for example, you have thrown away information. If this is necessary for you or not may depend on the particular optimization problem at hand. Yes. Okay, but general message, yes, one could also think about doing additional learning afterwards, but since the evaluations were, let's say, sufficiently cheap, and since we had a lot of constraints and other things, we felt that this swarm optimization is the easiest way to go. And very practical reason, the industry partner uses it anyways. So. Okay, then I have -1 minute left. Okay, that's plenty of time. Okay, I promise I will try to make a very brief summary of this story, and I will just do it conceptually. So this was also an industry-driven project. So the one before was with Mona Vorländer and Morten Huber. I forgot to mention their names. So this is with Vivek Parekh from Bosch. So it's a very highly parameterized machine model. So I think 20 KPIs they looked at and over 50 parameters that you can vary. So it's very highly templated. And this was supposed to be optimized. And a few parameters and KPIs are just mentioned here. So I will not go through them. So I just want to convey the message that practically relevant and sufficiently complex, such that I would have not probably done that at my chair if I've not had an industry partner who has all this already implemented and is able to do this. And now that's let's say a meta storyline. So what and how to learn. And I'd like to come back to the beginning where I made some claims about that. So now we have some input parameters, right? And then the usual workflows from that, you generate a CAD model, then you mesh it, you do finite elements. Then there are some intermediate quantities of interest. I call them intermediate measures at some point. Then you do, based on those, you do post-processing. The post-processing may also involve some of the original parameters. And this spits out and I think it were 20, if I'm not mistaken, 20 KPIs that I have as some constraints in my optimization problem. Now, what are the bottlenecks of this workflow? So obviously, this is a bottleneck, yes? So this post-processing takes maybe minutes, but that takes up to hours or more. So that's the expensive part. So now what to learn? That was now the question, and we tried several things, and that's essentially the story, but let me show you some pictures. What was the winner according to our studies? So the most obvious idea could have been you try to learn the mapping from those parameters immediately to those post-processing quantities, yes? So that's like the very traditional way. You do that with neural networks, you can do it with something else. In this case, and we will see in a minute why we use neural networks, but you can do that with any technique and you just learn this. But that turned out to be not very flexible and that these y variables, maybe not very physical. And then we came up with this approach, which is just a small variant, but it was really much better, where you do not use the neural network to directly predict the quantities of interest, but you just learn, let's say, a few quantities of interest from which you can deduce your post-processing quantities. Then you still have to invest a few more minutes to do this physical, let's call it physical post-processing. So the whole workflow becomes slightly more expensive, but you still reduce it by the biggest fraction, which is like the solution of the PDE. But since these values are deduced from those guys based on simple formulas, you still keep the physics in. So now in the learning process, you just have to make sure that those guys are, let's say, physically reasonable, and then those just follow along, right? Because they are just post-processing quantities. And this was, in our tests, a much more successful approach. What we also tried in this work, that was the very first idea, if you have very complicated CAD models, and it may be the issue that these template-based CAD models are even differently parameterized, right? Even if it looks the same, the parameters may be different because a different designer has created those parameters. And then the issue is, okay, how to use that in learning? And the first idea was that we create pixel images, which in 2D is supposed to work nicely. Well, in 3D, maybe questionable, but in 2D, we expect it to be nice. But this turned out to be not very successful. You need very fine resolution, which really increases the parameter space you have by a lot. The only way to make that somehow work was in the end to feed those parameters and the images. Then we could get proper prediction quality. So this approach, at some point, we dropped essentially. What we replaced that in the end by an approach using a variational autoencoder, and I think it's like a running joke. Matthias will tell you all about it, about autoencoders. So, which essentially figures, I mean, if you have now different parameterization, so the autoencoder is then supposed to figure out what is the latent space behind, right? Because you have different parameters, but essentially they will vary geometric entities. And there is a deeper connection that maybe a human may not easily see, or it may take a lot of derivations to get it, but the autoencoder shall be able to deduce this. And this indeed worked very nicely in our studies. Okay, yeah, so there are some examples. As I said, I'm out of time. I just want to end here. So that was then the final result, right? Based on this autoencoder workflow with this physics-informed kind of post-processing step, where we could now optimize over differently parameterized geometries and even across different technologies. So there were really different topologies, different templates with different topologies that we could optimize, and that's the result where we did the optimization, and you very nicely see the Pareto front over there. And you see that on this Pareto front, there are, let's say, single V and double V design. Okay, that depends how many magnets you use or how they are shaped. And you see that really this method was able to learn from, no, these are the optimization samples, not the samples we used for learning, but it could really find a Pareto front that consists of both kinds of topologies. Okay, I think, so the main conclusions I want to convey here is that, or the main storyline of the talks I gave you. So the stuff that we mainly did was focusing on learning KPIs. I discussed several methods. In this case, we took the neural nets also because we wanted to do images, and the images are really way too large for any other approach. That's why we went down this convolutional neural network route, and we were quite happy. But we didn't do any theory, no guarantees on anything. Well, it did work nonetheless beautifully, I have to admit. And then I showed you in the context of yield optimization how Gaussian processes could be arranged and could be used, but all based on quantities of interest. And I think I should close now. Thank you for your attention. I suggest, in the interest of time, that the online people please write me via email or Teams, contact me over there if you have questions, and the audience here in the room, I mean, I will be here for the coffee break and so on. Please just come to me, okay? Thank you.